Hello, I'm Mr. Hotelling, and welcome to this installment of Numbers in Physics and Chemistry. In our first installment, I want to give you an overview of this series, as well as address our first topic in the series. What do we need to know about numbers in chemistry and physics? Our series addresses the following topics: different types of numbers, discrete and continuous, where do the numbers come from? And there are 5 different sources. What are the different ways we use numbers in our common usage or colloquial usage in math and science and how that's different? What are the numbers and how do we write them? And how do we write large and small numbers using scientific notation? Now, in most of your mathematical experience, you've come across a table that looks like this: complex, imaginary, rational, null, integers, wholes, naturals, irrational, and so forth. This is something that's important to mathematicians, but it's not something we worry about so much in physics and chemistry. Our focus in physics and chemistry is how we use numbers to do our science. And the first of those issues comes to understanding the difference between discrete and continuous numbers. So let's begin with an example here. If we look on the left, we see we have these eggs, and we can ask the question, how many eggs are there? And of course, we would notice there are 1, 2, 3, 4, 5, 6. If we were to have more eggs, there might be 7. If we had fewer eggs, it might be 5. And so we know there are 6 eggs. And that number could vary, a plus or minus of 1. The way this number 6 changes, is by ones. This is an example of a discrete phenomenon. Now we could look at the picture on the right and ask ourselves, how many eggs are there? Well, at first that becomes very difficult. How do you do this? Because we can't count. So how we might answer that question is to use another concept like mass measured in kilograms or volume measured in cubic centimeters or milliliters. We might use those concepts to get at this by comparing them to some kind of standard and making a measurement. We could go about eating these eggs or taking out portions of these eggs, but the sizes of the portions we might take out could be arbitrary. And there could be an infinite number of possible sizes these could be determined by. The size could be determined by. So if we ended up with some number, say 128, the plus or minus is some other number, what we would go up or down by, that has to do with the scale we used. And let's say we were using milliliters. We might have 128 plus or minus 2 milliliters. So, as we said previously, this is an example of something that's discrete. It can change in size by only a definite sized amount, whereas the amount of these eggs could change by an almost infinitely large number of possible sizes. And that is where we use the word continuous. This can be continuously broken down into smaller and smaller and smaller and smaller pieces. So to summarize the difference between discrete and continuous, discrete things are like integers. There's only distinct values. But it turns out those values are not limited to integers. The example I've chosen is integers, but not all examples are integers. They can be any kind of number. And for example, we can have any number of eggs that can be cracked, but you can't crack 0.6 of an egg. And again, discrete things are things that could be counted or whole number multiples. And to give you another example of an exact number, We have a number pi that most of you are familiar with. Well, we could have 1 pi or 2 pi or 3 pi. In this case, we have exact multiples of a definite or exact number, pi. On the continuous side, we have numbers that are infinitely subdivisible. We can have any number of eggs that are scrambled, and any amount can be served or eaten, not just a whole number. Discontinuous things can't be counted. They must be measured by comparison to some standard, and that's what measurement is. So those are the types, and his example of discrete and continuous. Now, the importance of this has to do with a brand new concept to most of you in science, which is uncertainty. Uncertainty deals with how well we know or can trust a numerical value. Now, we can, of course, take the concept of uncertainty outside the realm of science and say, can we know a historical fact with some degree of certainty? We have uncertainty exists in other fields besides math and science, but it has particular definitions and applications in science. But it's how well we know or can trust a numerical value. And it turns out that when it comes to whether something is a discrete or continuous, some entities can display a duality. And let me give an example. If we were to go to the store and buy cement blocks, well, we could buy 1 block, and we could buy another one, and we would buy 2 cement blocks. So the number of blocks that we would buy would change, or we could change or vary it by 1 block. But if we then took these blocks home and went to build something, we could use them and break the blocks down and use portions of the blocks. We can only buy them in a discrete sense, but we can use them in a continuous sense. So here we have 1 block, and we'll use part of this one, which I'm going to say is about 0.7 blocks. So we might say the number of blocks we used is 1.7 plus or minus some amount. Plus or minus some amount, which probably, giving my estimation here, we might say plus or minus 0.1. And this is what we would say is our uncertainty. And this is our uncertainty. So what we said at the beginning of this slide is that the importance of knowing this in science, the difference between discrete and continuous, has to do with identifying and quantifying the uncertainty, how well we know something. Now, it does turn out that most of the time, or much of the time in physics and chemistry, the numbers we use are continuous, but not always. And it depends on the subtopic we are looking at in physics and chemistry. And lastly, a little historical context. One of the most important figures in all of the physical sciences was Sir Isaac Newton in the 1600s, who invented calculus and much of what we ascribe to modern physics and the basis for the modern chemistry, which would come later. He developed this idea of continuous world. And basically, he said that time and space and all other kinds of physical attributes were continuous. And that formed a worldview that lasted for centuries through the 1600s, 1700s, and 1800s. And along near the end of the 19th century, the 1800s, Max Planck and others, Max Planck laid the foundation, and Einstein and Bohr and many others during a very brief period of about 30 to 40 years during this window, started to realize that the universe doesn't operate in all aspects on a continuous basis, that there is this discrete nature to some attributes and some phenomena. That came to be known as quantum. And many people have heard of quantum mechanics and quantum physics, and what this idea of the quantum is about is in contrast to a continuous world. And this was truly, truly mind-bending and was a very difficult transition for the scientific community to make, but has led to tremendous gains in our scientific knowledge today. I've included a little bit of a reading here for you if you want to pause the video at the end to look at this to give a little more clarity on this. That gives a little bit of background about discrete mathematics and Newton, and from a modern university setting, we have this equivalence of quantum and discreteness. And if it's another way to help remember the idea of what discrete and quantum is, because it's so counterintuitive, is the idea that things exist or behave in lumps as opposed to a continuum. In our next installment, we are going to look at where numbers that we use come from. In physics, in chemistry, we have numbers that appear in front of us, and they come from different sources, and of course that also affects how the uncertainty is determined with those numbers. The first of those 5 sources, counts, will be the subject of our next installment. Thank you for watching this installment, and I look forward to seeing you in our next episode.